Hello, physics class. You should be viewing this video on Monday, April 13th, and I hope you had a great day off of school on Friday and a wonderful Easter. And we're going to just press on with this material. We're going to be covering the theory content of section 11.1. You already took notes on it last week, which is awesome. And so if you can have your notes available, I know I have mine, and just follow along and update and add as necessary. And then there will be a little Google form for you to respond to this video on after you finish watching the video, obviously. So let's start talking about the many forms of energy, which is what section 11.1 is all about. And so according to the work energy theorem, you'll remember that one from a previous chapter, doing work on a system causes a change in the energy of that system. And so work and energy are clearly related, and we're going to be exploring more about that later on. But first, we're going to talk about some of the different types of energy that you can have. And so I've just listed a few of the forms of energy that are very common. And we started talking about kinetic energy in chapter 10, and we're not really talking about kinetic energy that much in this section, but we will be relating it to potential energy coming up very soon. And so, of course, that's the formula for that is 1/2 mv squared. And so that's going to come up again later on. And then today we're going to talk a lot about potential energy, but some of the other forms are mechanical, thermal, light, sound, nuclear, and electromagnetic energy in general. So we'll be talking a lot about potential today, but just keep in mind that these are all different forms of energy. Okay, so let's start talking about potential energy. Just in general, the symbol for potential energy that your book chooses to use is capital P, capital E for potential energy. I do want to point out that some textbooks will use a capital U. So should you go on to take physics in college, you might have to shift gears and start using capital U instead of this. But we're going to stick with this because this is what your book uses as well. And then since it is a type of energy, of course, the SI unit is going to be a joule. And then we're going to talk about these specific types of potential energy. And don't worry, we're only going to do a formula. We're only going to solve math problems with a formula for gravitational potential energy. I will give you the formula for rest energy, but we'll just talk about theory for the bottom three. So let's start talking about gravitational potential energy. This is the one you're probably the most familiar with, and it's the energy that something has due to gravity. And for that to be a factor, it needs to be at a certain height above what you say is the reference level. So again, gravitational potential energy is energy stored due to height. And so it has the potential to fall. So it's got the possibility that gravity could be pulling it down. And so it really depends on what you say is the reference level. And so the reference level is whatever you say the height is equal to 0 at. So let's say that I take this pencil, and it's really hard to show a lot of things around here, but let's say that I have a shelf, and this is a shelf, and I put the pencil right here. You can't see it, but I have a desk underneath this, and the pencil would have a certain amount of gravitational potential energy in reference to the desk, and I'd have to measure whatever the height from the top of my desk is to here, and I would incorporate that into the formula. But then I could also think about it with the reference level being the floor. And so the floor is much further down than the top of my desk. And so you can see where the height would play a big factor in this formula. So, this helps. There we go. So you actually have two different formulas depending on whether you're given the mass of an object or the weight of an object. And so if you only have mass, then you need to incorporate little g, which is acceleration due to gravity. And we're going to, unless otherwise stated, we're going to pretend like our problems are here on Earth, and we're going to use the value 9.8 meters per second squared for little g. And so if you were given the mass, it would say something about it being in kilograms, hopefully. If it's in grams, you know what you have to do, convert it to kilograms. But this is the formula that you would use. And your height needs to be in meters for this formula because you want it to match the units that are in a joule, which is a kilogram times meters squared per second squared. And so keep your units consistent, please. But if you're just given the mass in kilograms, you would use this top formula. And then if you're given the weight of something, it would be in newtons, and it already has G factored into it. So you don't want to double factor it in. So if you're given the weight in newtons, remember F sub G stands for the weight of an object. You would just simply use this bottom one. And since G is already factored in, you can just multiply that by the height above your reference level. So that's, we'll be doing math problems tomorrow, or actually maybe the next day, on this specific thing. And then another type of potential energy that we're going to be talking about is elastic potential energy. And we don't have any formulas or anything associated with this, but elastic potential energy is energy stored due to an object's change in shape. And you could see this like on a spring. So some springs are naturally going to be meant to be compressed, and then when they're compressed, they're going to have that stored elastic potential energy. And then some strings, if you stretch them, they'll pop back into place. And some can do both. But you can see how energy could get stored in a spring. As soon as it's released, it's going to release that elastic potential energy. Another thing is like the simple hair tie. Obviously, if I stretch it, I'm going to give it gravitational potential energy. And did I scare you? Hopefully not. And then another timely example is this face mask, elastic in the little part that goes around your ears. So yeah, that's a corona example right there. So that's elastic potential energy. Another one that you may have never even heard of before this chapter is called rest energy. And this was thought of by Albert Einstein. He was the one that first proposed this. And his idea is that everything that has mass has energy stored inside of it, and that energy is proportional to its mass. And so a big, huge rock would have a lot more rest energy than a tiny pebble, because it simply has more atoms, it's got more chemical bonds, it's got more energy inside those atoms because it has more atoms. And so it's the idea of that. And the symbol for rest energy is E sub 0 or E sub naught is the way a lot of people will say it. And it's still a type of energy, so the unit is joules. And then it's basically the general theory of relativity. Usually we just write E equals mc squared, but since we know we're specifically talking about rest energy, I went ahead and put the little sub naught on it. But this energy is calculated by the mass of the object and times the speed of light squared. So that's the way that you calculate this. We're not actually going to be doing calculations on this, but this is the theory behind it. And then we also have chemical potential energy. This is energy that's stored within atoms themselves and also associated with chemical bonds. And it's the reason we can have like nuclear bombs and things like that. We used to think that energy could not be created or destroyed. Now we know that energy can be converted into mass. And we also know that mass can be converted into energy. It's pretty wild. So anyway, chemical potential energy is another one. And then this is not a type of potential energy itself, but I want to talk about the difference between, going back to my original list of all the different types of energies, I want to talk about the difference between thermal energy and mechanical energy, because they both involve potential plus kinetic energy. But when we talk about the thermal energy of an object, we're talking about the energy of its particles that are inside of it. And so if I just have like a pencil just sitting there doing nothing, it has thermal energy because it has mass and it has moving particles. And the warmer this pen is, like the higher the temperature, the more those solid particles are going to vibrate back and forth. And so thermal energy will increase if you have a temperature increase, and also the more mass, the more thermal energy you would have. But it's all like related to internal particle motion, whereas mechanical energy is also potential energy plus kinetic energy, but it's related to them on the macro level. And so we're really associating it with the movement of an object. And we would think of mechanical energy like a fan spinning or a garage door opening up and things like that. So it's on the macro level, whereas the thermal energy is related to the energy of the particles inside that make up objects. So I wanted to make sure I went through those couple of distinctions with you. And then just in general, energy is transferred from one form to another all the time. Like for instance, radiant energy from the sun is absorbed by plants, and they have the chloroplasts, which contain chlorophyll. They can do a process called photosynthesis, and they can store that energy in the form of sugars that can be used later for food for the plant. And so just radiant energy being transferred into stored chemical energy, that's one energy transfer. Another one is electricity. When you plug in your a toaster or something like that, you can transfer electrical energy from electricity to thermal energy and a little bit of light energy too. Or you can plug in a hair dryer, or you can name 10,000 objects you could probably plug in. But we convert electrical energy to other forms of energy all the time. Electrical energy could be converted to mechanical energy. Like if you plug in a fan, it's going to make the blades spin around. Another one is we can convert kinetic energy to thermal energy. You just rub your hands together. Go ahead, you know you want to. But as you're rubbing your hands together, you'll notice that it heats up. And so you're converting some of your kinetic energy to thermal energy, which is heat, and also sound too. So there we go. So I've covered a lot of the stuff that's in chapter 11, section 11.1, and then we'll do some math problems, and then we'll have like a little practice thing, and then you can have a quiz. As always, if you have questions, send me an email at sdixon@evajax.com, and I hope you're doing great. Continue to write in prayer requests and comments, because I do read those. I do pray for you, and I really, really hope that you and your family are doing well, and I hope we're able to get back to school and get out of the house soon and back to normal. That would be awesome. So take care and stay safe.